I guess I should not look down when I'm talking to the microphone. So I'm here to talk about an object-oriented finite element program that we're putting together at the National Institute of Standards and Technology. All right, this really is stupid. So the scope of this project is we wanted to provide a tool for material scientists. The general motivation was many years ago, some investigators, postdocs at the National Institute of Standards and Technology were trying to make a model of a microstructure that they thought was interesting, and they were trying to do fairly simple finite element stuff, mechanical properties. And they were interested in, they had the spatial microstructure, and they wanted to make a mesh that matched the microstructure, and they wanted to make a custom constitutive rule. They wanted to have particular properties in the constituents, and then the question was going to be, well, what are the properties of the aggregate, the whole system, as a function of the properties of these constituents? And it was just crazy hard. The meshing tools that were available for the commercial finite element tool were not well adapted to microstructures. This is this slide here. So it was hard to mesh, it was hard to add the constitutive rules, and even if they had been able to do so, a lot of what the tool was doing was kind of a black box, and they wanted to be able to tinker, and they wanted to be able to reproduce their results, or at least know what was going on. So the solution was, well, we said we should write our own tool. How hard could it possibly be, right? These are the amateurs who don't know how hard it is. And so we did that, and along the way, we knew that we wanted to use a methodology where we would have a relatively high level, use an existing scripting language to tie together some high performance, probably C or Fortran code. And then we made the call, I think, in around 2000 to use Python. The alternative at that point was basically TCL, probably. It was a good call, and we've stuck with it since then. But we are, I think, so some of the speakers here have talked about the relative vintage of their software. We almost predate Python. We went with Python 1.5.2 was the first version, and at one point I was the Python expert on the team because I had actually run Hello World in Python and nobody else had. So again, I can't help but apologize for the awkwardness of this. So this is kind of the scope of the problem. This is the math and material science. It's pretty straightforward. What you have is you have some field represented by the letter phi there, and you have some equation for the field as a function. So the field evolves according to some second order in time coefficient and some first order in time coefficient, and a constitutive rule and a forcing term. And the constitutive rule is the most important thing, is the thing in yellow there. Constitutive rules tell you how the field maps to what in OOF terminology is called the flux. And the flux is kind of the response function of the system. So this is very schematic. The typical mechanical properties example is where the phi field would be the displacement field, and the sigma field would be the ordinary mechanical stress. There's a couple of other examples mentioned up there, I think, which I actually can't read from here. Going from math to finite elements is pretty straightforward. You just integrate the weak form, and you get you do this discretization by integrating your continuum fields over shape functions, and then the integral of the field with a shape function, or the integral of the equation with a shape function gives you either an equation, either a row or a column in a giant matrix, and then the rest of it is basically matrix mechanics or matrix analysis. Where are we here? So this is more or less the use case, or the operation of the software. You start with a micrograph, you segment the micrograph, you mesh the segmented micrograph, and we have tools for that, and then you run the finite element code and you analyze the results. And we also have a sort of conceptual framework that we work within that helps to kind of manage the complexity of the software. So this is kind of based on a sort of word processor type model where this is kind of similar level of complexity where you have a lot of components. So the microstructure, as you can see there, is sort of like the document, and then there are various pieces. The images are parts of the document, and then there's the skeletons, which are the skeleton is the finite element sort of architecture without the physics in it. That's something that you can manipulate separately, and you can have many skeletons for a given microstructure, and then the actual mesh is with the skeleton with the physics, and that's the thing that you can actually do finite element analysis on. And so we find as we go through this that we're overloading terms from time to time. So in the OOF context, for example, a field and a flux and a skeleton and a mesh have specific meanings that they may not have in other contexts. So one of the steps is image segmentation that we do. We have a pretty broad sub-project within the OOF project that is specialized in image segmentation. And in this case, ideally, we would like to be able to automate image segmentation completely. That's an incredibly hard problem, not just for us. But we have a lot of powerful tools, and we also rely to some degree on the user. So the OOF user is assumed to be kind of a domain expert in the science of the material that they're analyzing, and they know better than anybody in the world what the right segmentation is. So they can recognize it when they see it. So if we give them some tools where they can kind of go in the right direction, they can find a good segmentation. And then for the finite element geometry, we have a meshing scheme that involves overlaying the segmented image with a space-filling, well-formed mesh. And then we have a number of mesh transformation rules where you can subdivide elements or move nodes around according to various criteria. And the rules, all of the rules preserve the well-formed space-filling character of the mesh. And there also are numerical tools to help assess the quality of the mesh. So the primary things are we have a de facto artificial energy function that we use that will tell you there's an energy penalty for elements that are too long and skinny, that have bad aspect ratios because those screw up the finite element convergence, and there's an energy penalty for elements which are inhomogeneous. If the material boundary goes right through an element, then that means that the skeleton or the mesh is not matching up with the segmented image. And so again, in this case, the user is not expected to be an expert in meshing, but we give them the tools that they can assess the meshes reasonably well. For the finite element geometry, that's the one I just did. One of the problems with this particular scheme is that I have some slides here that are supposed to be hidden, and they're not hidden anymore. So constitutive rules are a very important part, the ability to customize constitutive rules. So I just want to take a second to define what a constitutive rule is. It's this, as I said before, it's this mapping between fields and fluxes. It tells you how a given material behaves when loaded in a particular way. We have a number of built-in constitutive rules for all the sort of simple things, linear elasticity, thermal conduction, chemical conduction, all this kind of easy stuff we've done. And we have this extension framework, which I will talk more about in a minute. So I'm going to skip over some of this. Also, we have some pretty advanced linear algebra. Again, this is a thing where we think we're making a pretty considerable contribution over someone who would write their own finite element code. We're not doing better than the commercial finite element codes here, but we think we already have other advantages over the commercial finite element codes. And here, we've paid a fair amount of attention. There are people at NIST who are experts in GMRes and various other kinds of solvers, and so we have some, we think, pretty good libraries. So again, if someone is again, the whole goal is to bring enormous computational power and good resources to somebody who is a material science expert, but who doesn't want to code or doesn't want to code very much. All right. So this is more about that. I guess this is. So in the analysis of the results, there's a fair amount of built-in tools where you can, of course, make contour plots of the fields and contour plots of the fluxes, or if they're vectors or tensors, you can make contour plots of their invariants. One of the puzzles here for the OOF team is kind of when to stop. We don't know if we've solved that problem. We built a bunch of tools, but sometimes we get requests for people who would like to be able to, sort of take higher order moments of the statistics of various fields. And if anybody asks, we'll probably do it if it's something that's reasonably easy to do. But at some point, I mean, you have to wonder about when we should hand this off to a better tool that really can do a better job. I think that one was supposed to be hidden, but it's worth mentioning that we have both a GUI front end and a menu. scheme, and actually, in light of the previous talk, one of the things we did for our menu operations, the arguments to the menu system are objects which, believe it or not, we also call parameters, but parameters are type-aware container objects. I don't think they're quite as clean and nice as the parameter talk that we just saw, but it's clearly, this is a solution that has been reinvented several times. So the architecture was, as I discussed a little bit earlier, it's Python and C++. This is partly an artifact of the time at which we made the various calls that we needed to. We don't actually use the SciPy and NumPy libraries, although we are always keeping an eye on them, and we're very impressed with what's going on. There may be a time when we will make the jump. But we have a top level that is Python, and we've enjoyed the advantages of Python enormously. We can rapidly prototype. We can just try stuff and learn very quickly whether it works or not. We have most of our numerical stuff in C++, and they're tied together with Swig, which has been great. So the other point about Swig actually is one of the advantages of this is we have occasionally in the application had issues where we run into performance problems in some of the Python, and one of the things you can do with Swig reasonably easily is move the C Python boundary around. So if you find, you can move it either way. If you find you're having trouble, if something's, you're finding you're having to make a lot of changes in something and it's really more dynamic than you expected it was going to be, you can move the Swig boundary down and pull that up into Python. Or you can go the other way if something's not performing well enough, but it's reasonably static and the dynamism of Python isn't doing you any good there. You can change where you put the Swig stuff and move the boundary up. So that's been handy. We've done that more than once. So it mostly runs on Unix-like systems. There's no Windows version. And this actually slide is slightly out of date. The 3D is very much active, the thing that's at the bottom there. So the current release is 2.1.7. It's a two-dimensional code. I don't remember what's on there, and I can't see it from here. So we have orientation, sensitivity. We're doing some work with plasticity and some fairly serious and interesting nonlinearities, which I will talk about more in a minute. And the major focus on development at this point is 3D, and also there's an effort going on with surface properties. One of the issues with finite element code sometimes is when you have rapid transitions, if you can explicitly model something with a surface element, you can sometimes do better than if you try and actually do the full real space model. So that's an abstraction that we're working on implementing. This is my electron backscatter orientation example, which I think I will not spend much time on. That's another one. So this is the example that I really want to talk about because this is great fun. So we have this, extensibility scheme, and we had a nonlinear property API, and about a little over a year ago, a graduate student from Northwestern University emailed me and said, I have this material and I want to fake plasticity, and the way I want to fake it is I have this constitutive rule called Ramberg-Osgood elasticity. And what Ramberg-Osgood elasticity is it has a low displacement curve that is like the one you see on there. When you strain the system, initially there is a lot of stress, and after you get past a certain level of stress, the additional stress gets much lower. And so that's indicated on those two curves. The one curve is a flipped over version of the other one. The one on the right is the more conventional low displacement orientation, and the one on the left is the way in which the Ramberg-Osgood elasticity is actually typically written. I thought this was great. It was like I had never heard of it, but it was magnificently nonlinear, and I thought, well, this is a really good test of the nonlinear property API for OOF, so let's give it a go. And so, of course, I prototyped it out in Python. So here is the actual math, and I don't mean to frighten people too much with the equations. The initial one here, look, I can point at this because this is all screwed up. So the first two terms in here are just ordinary linear elasticity is typical Hooke's law, and then there's this other term that says that the amount of strain that you have for a given amount of stress is this Q over some scale factor to some power. What was that about? Okay. Times a tensor that tells you how much of this is deviatoric. Thank you. And the Q factor is written here. It's essentially the magnitude of the deviatory part of the stress. So that's a lot of, that may be a little bit of word salad for some of you. Stress is a tensor. The deviatory part is basically the part of the stress that doesn't have any compression in it. So if it's sheared in any direction, this number is large. If you just press on it or pull on it uniformly hydrostatically, this number is small. And the coefficients there are the ordinary coefficients. So this is a reprise of the constitutive rule illustrating one of the complications, which is that it's an implicit, so in the OOF scheme, what we want is we have constitutive rules that are stress as a function of the strain or stress as a function of the linear combinations of derivatives of the displacement. And this particular rule doesn't do that, it goes the other way. But that turns out not to be a problem for us. Handling this, again, Python was instrumental in being able to just try this out. So, can we just solve this implicitly by doing a little Newton-Raphson inside the constitutive rule? How horrible is that? And the answer, it takes 10 minutes to try. Well, all right, it took half a day. Turns out that works very well. And so I did put together a microstructure that does this, and this might be the, excuse me, kind of the hello world of material science, if you want to think about it this way. The point of this example partly is to illustrate the implementation of this Ramberg-Osgood plasticity rule, but also this is a microstructure where, obviously synthetic, I made this up, I did this in a drawing program, where the area fraction of the blue and the gray parts are the same. So if you had something that assessed this material as a function of area fraction, you would make a serious mistake. And I'm going to go down to closer to the punchline. I guess not quite that close. So all four possibilities were explored so if everything is linear, that's one system. If the inclusions are nonlinear and the matrix is linear, that's another one. If it's the other way around, that's another one. If everything is nonlinear, so that's the four possibilities for nonlinear, linear, and nonlinear. Again, I cannot help but apologize for how awkward this is. So here are load displacement curves for each of these combinations, and they go the way you expect, or at least they went the way I expected. The fully linear system is the stiffest, the fully nonlinear system is the softest, and I was very gratified that my intuition was met, that the system with the nonlinear softening matrix is softer than the one with the nonlinear softened inclusions, because the matrix percolates across the whole system, and so when that can all go soft. So that when you're applying tractions on the boundaries, that's softer than the other way around, even though, as I said, in both cases, the area fraction is the same in both cases. So again, the reason this is the hello world of material science is the fundamental axiom of material science is that structure controls properties. And here we see the two different structures. Everything is the same about these except the structures, and that's what's controlling the properties. So that's a nice little story that we can tell. It's an OOF story, it's a mechanical properties story, and it's also a Python story. And of course, this isn't something I do by myself. This is our team. We have a number of contributors who are currently contributing, and a number of former contributors. We've had many postdocs and summer students contributing enormous value throughout the years. So, thank you, and sorry again for the display horror show.